a set of spins in the goal of simulating it. And quantum computation has developed a large number of tools, such as the gates and the circuits that Seth introduced to you, to be able to take a known system and make it model a different one. What I'll be speaking about is how these control techniques actually allow us to elucidate and control even an unknown system and make it behave in different ways that allow us to elucidate its behavior. And I'll begin I'll give you 3 examples, and I'll begin by giving you one simple one, which reaches back into 1999 and an experimental result then. And this is one based on the idea of quantum error correction, to be able to control and correct for the most basic of quantum mechanical behavior, which is T2. So if you have a qubit, then it will shrink in its block sphere due to the undesired interactions with the rest of the environment. And this loss of coherence can be undone by using quantum error correction. A very simplistic version of this scenario is dealing with just a single spin. And in this case, as I just mentioned, if you consider the following experiment, where we start with an input state shown on the left, where we have a block sphere that is completely round, spherical. Then after sitting in an interaction with an environment for a short period of time, what happens is that the coherence between the vectors in this xy plane get lost. And therefore, the block sphere starts to shrink when you consider its density matrix. And this shrinkage in the xy plane eventually gives you a fixed set of points, which is the vertical set of the line between 0 and 1, which is a statistical mixture that is a purely classical state. So suppose we do this experiment, we would prepare some state which is sitting along the block sphere at a certain angle. We then let it evolve by getting compressed by T2, and then we flip it. At that point, when we measure the magnetization in the xy plane, the length of that vector will tell us how much it is shrunk by. Now, mathematically, this is known as a density matrix being shrunk with the off diagonals, which represent the coherence tending towards 0 in this exponential way shown here. And therefore, this behavior, mathematically modeled as the loss of the off diagonal coherence in the system, can be analyzed both experimentally and theoretically. So suppose we take a single spin, this loss of coherence theoretically should result in a sequence of measurements as shown here, and experimentally we find a very good agreement with that theoretical prediction when taking a single spin and watching it. So the outermost curve is when you wait nearly 0 time, then as you wait longer and longer, the curves come in and shrink to become this ellipsoid.
Slightly more the projector.
Now, if we, instead of using a single bit, use 2 quantum bits held together, then we can start to use the ideas of information. The quantum bit that we want to think about is a collective degree of freedom between the 2 qubits, and not just a single spin at this point. And when we do this, if we encode by taking the block sphere that's on the left-hand side of this diagram, and turn that into a collective state of the 2 spins, here shown as the 0, 0 plus 1, 1 state, and the 0, 1 plus 1, 0 state. And now the qubit is a collective degree of freedom between those 2 basis vectors. What happens is that after that evolution, when we decode by tilting the spin back and then measure, we find something completely different in behavior from before. Because this is a code which has allowed us to preserve this spin information in a degree of freedom that is immune to the environmental behavior So one can turn on and off undesired terms in a Hamiltonian in this manner. That idea is one of the most important facts that was used in our demonstration of the Shor factoring algorithm, which involved this sequence of pulses shown here. In this diagram, I show 7 different spins vertically, and horizontally I show the different pulses that were involved in forming this experiment. The 90-degree pulses are shown in red, such as the ones in the upper left corner. And by and large, what you see is a great variety of blue pulses. And these blue pulses are 180-degree pulses, which perform exactly that refocusing, turning off of the interactions that I just described mathematically. And the impact of this back on the field of physics has been amazing. The concept of refocusing has now been extended to be used in other physical systems, as shown in this view graph, work at Saclay, showing its application to the superconducting systems. So a superconducting circuit, such as the one shown here, with a Josephson junction, the large square, allows us to create a coherent state of evolution, coherence of evolution, where the system evolves rapidly back and forth between 2 levels of the Cooper pair excitation. And as this system interacts with the environment, you can see that there's a decay in the spinning that is shown in the top right-hand side, spinning back and forth. And it decays with this time scale of about 350 nanoseconds. But if you apply a sequence of pulses instead of just a single pulse, where one introduces this high pulse I show here on the bottom right-hand side, then the coherence time gets extended to 500 or so nanoseconds, and now people have been able to extend this to on the order of a microsecond, which is even more impressive. And this concept of refocusing as dynamical control for systems that are outside of quantum computing has been extended not just to superconductors, but also now to ions and neutral atoms and a variety of other very quantum mechanical, atomic, and molecular systems. I want to, in this particular case, pose an interesting question to you, because this is a frontier of research. The reason behind why this works is because the sequence of pulses that are applied are known to average away an unknown Hamiltonian, and that is shown here. Suppose one has a Hamiltonian that has an interaction between the system, sigma k, and the environment, E sub k. Then it is well known, theoretically in quantum information, that if one applies this evolution for a while along the x-axis, and then flips it to be along the y-axis, and then flips it to be along the z-axis, then the net evolution turns out to be 0, when you add a little bit of identity to it as well. And that is refocusing, generalized to any interaction. What is interesting to me as a question is if there are pulse sequences analogous to this, which average away to interactions that are known but non-zero. And if one were able to achieve this, then you'd be able to create a new approach to building systems that can perform operations robustly, so that they could interact with the theory, for example, of fault-tolerant quantum computation, and allow us to use these ideas of quantum control robustly in other quantum systems as well. Okay, so that is my second example. And now let me turn to my third example of quantum control ideas from quantum computation. This third idea is the notion of composite pulses. And this is a field that is very old in the art of nuclear magnetic resonance, but in terms of quantum computation, it's relatively new. And the most exciting thing here is a recent addition back to the body of work of composite pulses that arises due to the theorems of quantum computing. The example I will give is a description of how this technique can be used to reduce to this classical mechanical system. So I'm describing mathematically this over-rotation in terms of an operator R here, with angle theta being the target. Epsilon describes the amount of over-rotation in a fractional percentage. Now, the solution to compensate for such unknown errors has been investigated in terms of magnetic resonance. And one of the most well-known sequences for correcting for these errors is known as BB1. And the sequence is to replace a single pulse, the Rx theta in this example, with 3 pulses, shown here, followed by the original pulse. So the total sequence here is rotation about the x, a rotation about some intermediate angle and axis angle pi and axis v, and then a rotation again back by 2 pi. And this can correct and reduce the error from a fractional epsilon to a fraction epsilon cubed, which is really tremendous. Let me illustrate how this works. Suppose I have a spin which I'm rotating, or a robotic arm which I'm rotating. We have 25% under rotation. So initially, instead of going all the way to the xy plane, it goes only 75% of the way. Then in this example here, I can't quite move my arm exactly like the example, but I rotate down, and then I rotate around, and I'm supposed to rotate around by 180 degrees, but I'm short again. Then I'm supposed to go back around this angle, this axis, by 2 pi, but I'm short again. And then finally, I'm supposed to rotate by pi around this axis, and I'm short again. But nevertheless, in this example, you see that the final point is very close to the y-axis where I had intended to go in the first place. And that's remarkable. No matter what initial state I am at, in fact, this works quite well. So ideally, this is what should have happened. I should have started by going from the z-axis all the way down. This would have been a perfect thing. I would have done 2 rotations, which would have done nothing, and then come back to the original place. And notice that the error is tremendously reduced from the original one. Here's what happens if one over-rotates. Now I start by going down too far. I rotate past pi all around. Then I rotate past 2 pi all the way around. Then I rotate past again. But as before, I end up very close to where I originally desired to go. And as I mentioned, this works no matter what the initial state is. Now, in the history of magnetic resonance, this level of reduction up to epsilon cubed was the absolute best people could achieve. There was no knowledge of how one could do any better than epsilon cubed. And you can imagine that when epsilon is very large, like 25%, reduce it down to 1%, but that may not be good enough. Suppose you want it down to a 10th of a percent or 100th of a percent because you need very precise movement or operations. Okay, especially when you cascade a large number of operations in sequence. So in the art of NMR, people have searched for better pulse sequences by using computer algorithms to explore the space of possibilities. But the space is enormous. There are far too many ways that one can cascade a sequence of pulses. And it's very difficult to cascade these pulses and still have an operation that works no matter what the initial state is. And here's where quantum computation and quantum information enters. This past year, we were able to develop a sequence of families of composite pulse sequences which correct up to epsilon to the n for any power of n at all. And this is quite remarkable in my view. Here's a sample set of results showing on the y-axis the amount of magnetization that goes to the proper final location, such as the xy plane, as a function of the amount of error in the epsilon, shown on the x-axis here. And with a single pulse, you get this normal cosine-like round shape. With the BB1 pulse, I discovered 5-speed windpress, you get a flatter shape that goes up or over and then back down. But then with these new sequences, you can get arbitrarily flatter and flatter and flatter. Of course, there's a cost. You have to increase the number of pulses. Now, instead of getting flatter so that you decrease the amount of error, it turns out that one of the nicest things about this theory is that you can also reverse it and increase the amount of error. So you can get this sharper and sharper. That is, if the pulses are wrong, then they get even more and more wrong. And this is probably going to be an extremely useful thing for magnetic resonance imaging, where you want to be able to distinguish as much as possible two nearby voxels of space, which have different magnetic fields applied to them. Okay. And so we show in this sequence that you get as narrow as you want, and as written at the bottom of the slide, the cost is n cubed. So if you want epsilon to the nth power, the cost is, from a constructive argument in simulations, n cubed pulse length, which is polynomial. And the secret behind how this works is perhaps the nicest thing of all of this theory. These are three equations which are illustrated. Suppose that you have an ideal pulse, which is RB, shown on the right-hand side. Let the actual pulse be this operator M. And what you would like to do is to cancel out the small error in this operator M by adding a small rotation before it that's ideal that just undoes the epsilon part. And how do you create this little epsilon part on the left-hand side is really the heart of the argument. And one can create a small epsilon rotation by rotating around 2 pi with this bad pulse. And this 2 pi pulse will be over-rotated or under-rotated by a tiny amount epsilon. And now you have a basis of small epsilon rotations. So what we know in quantum computing is that if you have the ability to rotate by a small amount, say in x, and a small amount in y, then by combining those small rotations, you can rotate around any axis by a small amount. And that idea is something that was explored by a student that Neil actually picked up as a freshman about 8 years ago, Aaron Harrow. And it involves a foundational theorem in quantum information known as the solidity-type theorem. Shown at the bottom of the slide, the equation says that if I have an x rotation and a y rotation that's small, I can compose them to create any rotation I want by taking the appropriate sequence of these rotations. And the solidity-type theorem applied to this composite pulse problem allows us to achieve arbitrary levels of correction. That is summarized in this graph here that shows the amount of error reduction on the y-axis and the amount of error on the x-axis in a logarithmic plot, showing that if we have 610 pulses shown in the red graph at the bottom, we're able to reduce the error to 10 to the minus 12, which is phenomenal. This technique works for a variety of errors, not just the over or under rotation that I showed you, and it is probably going to be quite useful not just in the art of NMR, but also in rather interesting mechanical systems, which is very unexpected. So I'm going to summarize my talk by giving you two things. In terms of recent progress along this theme, this is one of the nicest experimental results I've seen in recent times. It's a result using the composite pulse that I just showed you, BB1, to electron spin resonance. In the art of electron spin resonance, very few groups have ever applied composite pulses. But motivated by this quantum information result, this group, a collaboration between Princeton and Oxford, applied it to their spin system. And you can see that originally the oscillations, which is the spin coherence of the electron, decreases extremely quickly. But once you apply the composite of systems for fire control. Thank you.